So yeah, let's talk a little bit about, machine learning, because, AI has become such an integral part of our day-to-day lives. So, it's an obvious question that, why not also use it for astronomy? And yes, of course, we've been using AI for astronomy for quite some time now. And the same applies for detecting fast radio transients. So just before I start the talk, this is just massive disclaimer. I'm definitely not an expert on AI, but I'm happy to share some of the experiences that I've had so far while, delving into looking for fast radio transients in, and huge volumes of data that we get from radio telescopes. So I think just setting up the problem here, which I have already mentioned in my first lecture, which is that it's a needle in a haystack problem, right? So you're looking for something in a massive amount of data sets, which means that you are, in the end, in your pipeline, you're going to get an incredible amount of false positives, right? Because there aren't only signals, as we mentioned before, just from the astrophysical sources, right? There are so many sources terrestrial in nature that produce radio emission that will enter your radio telescopes because they are so sensitive. And this just to give you some rough numbers, right? So SK-MID, for those of you who don't know, it is a next generation telescope that's being constructed in South Africa and Australia called the Square Kilometre Array. And if you just take the specs for that telescope, you can see, I think the number that should terrify all of you is this one, right? So the prediction for that telescope is that when we'll run our real-time fast transient search pipelines on it, we expect to get 72 million candidates every day. Now imagine, so you looked at those plots, right, from transient X and your single pulse search.py, right? You saw the DM time plot to figure out if it's real or RFI. Imagine looking through 72 million candidates every day by eye and trying to figure out what is real and what is not. I mean, that's just not possible, inhumanly impossible to do, right? In a reasonable amount of time. And we are looking at things because these things, remember, these surveys nowadays have to run in real time, right? I mean, we can't save any of this data. The data comes in, we have to process it in real time. We have to try to identify candidates, whether they're RFI or FRB or an astrophysical source in real time, and then just get rid of the data immediately, because we are talking about petabytes of data being collected every day when these telescopes come online. It's just not physically possible to save that data. And so you can see that this is a very big problem that we have to solve, right? And so we definitely need the help of artificial intelligence, right? So it's an obvious thing to do. Why not just use machine learning to make our lives easier? And so I think what happened was that when people started to realize these things, we started with the simple things. So Ujjwal already talked about, clustering techniques that we use to reduce the number of candidates in a data set, right? Because your single pulse pipeline is giving you lots of hits at different dispersion measures at different times and different widths, because if it's a bright signal, the pipeline will detect the same pulse at slightly different DMs and time and widths as well. So you want to cluster them all together, as you should be able to identify them as one single candidate. But you can also then use this same kind of technique to classify candidates as real or spurious, right? For example, because now we have looked at enough data, we know what features identify or what features actually characterize an FRB or a pulse from a neutron star, and what features characterize an RFI from terrestrial source, right? For example, I showed you the dispersion sweep, that's pretty much a telltale sign for an astrophysical source. So then if you collect all these features together, you can then simply plot these features into, different features. So that's your parameter space. And then you can just make, or maybe some clusters will obviously stand out. So you can make some threshold cuts, right? So say if the DM is 0, it's definitely going to be RFI. Or if DM is less than 5, it's very unlikely to be a real pulse. I'm just kind of giving you some example. So just by, identifying some features of your data set and then applying some simple thresholds and filters, you can already get a binary classification to some extent of whether your candidate is real or something spurious. Now, of course, you can go one step further, right? You can put decision trees. So if you have too many features, it becomes a bit complex, right? So then you break down the problem into simple yes or no questions by building these decision trees and then coming to a conclusion of whether, things are real or things are fake. So one big advantage of something like this is so this is called something called as unsupervised machine learning, right? Because you're not you just need to kind of plug it. Like you plug it in, you know the thresholds, you put them in, you ask your classifier to be like, okay, these are the thresholds. So look at these features, look at the feature space, look at these thresholds. If it satisfies all these things, this is real. If it doesn't, not. Otherwise, look at the feature space, see if you can spot any obvious clusters. If it falls in this cluster, it's real. If it doesn't, it's something else. So these are easy to implement classifiers, and it saves a lot of time and compute power. So it doesn't need a lot of computational power either, right? So if you want to deploy these on real-time systems, it's easy. But there is definitely, so I guess before going into that, let's talk about the feature space, right? So just to give you an example about the features. So there was this very nice analysis that was done back in 2018 by Rob Lyon in Manchester. So they were trying to build, kind of a framework for what could a classifier look like for next generation radio telescopes, for pulsars especially. And so they did this analysis and they came up with these interesting so you can use statistics, right, and data to come up with these features. So for example, you can see, just to give you two examples, they use two of the metrics that they used as features were kurtosis and skewness. So a single pulse, right? Let's assume it looks like a Gaussian, right? So your kurtosis value for that pulse is definitely going to tend towards being leptokurtic rather than being platykurtic. Similarly, skewness as well, you assume that your pulses are symmetric in the sense it's a Gaussian. So if you're seeing something that's really weird and skewed on this side, like for example, something like this, you can use that skewness value, a negative or a positive value, to then try to see, okay, maybe if it's something that's positively skewed or has no skewness, that is probably closer to being a real pulse rather than something like this, which probably is something spurious or RFI. And so you can basically, so there are a lot more, as you can see, they're using a lot more statistical metrics here. And then you can combine all of those and then try to figure out classify things in your candidates, right? You classify all the candidates you're getting from your pipelines. And I think here's just an example of a real pulsar that was detected by this classifier and was assigned, or it basically identified this to be a real thing. So this is basically a known pulsar, so they tested it on some pulsar data. So again, so this is just to give you an example of what kind of features you can use from your data set to, basically build your classifier. But as I mentioned, there are some drawbacks here. One is that because the features, there are no hard thresholds here, there's always going to be, these classifiers are not going to be very accurate. So you're going to get a reasonable number of false positives in this case. And the other thing is that given that you have 72 million candidates to look through, even this is not going to be, I think, fast enough, given such, broad features, and which have, these features also have a little bit of overlap between things that are RFI and things that are astrophysical. And so I think given the current state of the art and, the advancement of technology and the insanely efficient hardware that's available to us, we can basically go do two things. One is dimensionality reduction clustering. So we are working with really highly dimensional data sets here, right? And so what you can do is you can then assume these data to be a superposition of all these features that you have decided on. It can be anything, or these dimensions. And then you can make a basis set of these superpositions of features. And that's what we call as principal component analysis, because once you project these features into this space, into a different basis set, which is a where the axes are basically a superposition of these different features, the eigenvalues of these vectors contain information about which, basically they contain information about what is actually in the data. Meaning that if there is some RFI in the data, one of those basis vectors, one of those eigenvectors and the eigenvalue will have the highest weight, and vice versa. So you can use these eigenvalues then to figure out basically again whether something has an astrophysical signal or something doesn't. Then you can again do things like you can take these, I guess, different features, right? Because we are basically projecting them to the different basis state. And then you can plot those against each other as well and do some clustering there. And you can see that, this has been done for some of these repeaters and non-repeaters. This is not for classifying them as candidates like astrophysical signals and RFI. What they're trying to do here is they're trying to see if there are distinguishing features between the observed properties of repeating and non-repeating FRBs. But you can apply the same techniques to your single pulse search pipelines as well. And you can see that if you do some clustering, some interesting kind of clusters come out. And then you can try to assess, okay, maybe, this cluster has some kind of a unique property then which I can use to filter out my candidates. But I think, according to me at least, the best solution at the moment is to use neural networks. Because all of those clustering techniques and principal component analyses that I showed you, I mean, yeah, they do work to some extent, but they're not going to get anywhere close to the accuracies that we need right now to do this they could be able to do it in real time, but even after that filtering, you'll still end up with so many candidates to look at, and you'll still not be sure about whether, if it's doing the right thing. So neural networks, again, are like I said, it's just basically a set of neurons, right? So similar to what, happens in our brains. And you can actually train, so now we are getting into supervised classification systems, right? So where you're doing supervised machine learning, where you have a data set where you know what your candidates are, and you feed it to this network, which is just layers of these so-called, I guess, neurons, which is basically our machines, right? It's like electronic computational neural networks. And each of these layers of neurons will basically learn something in particular about that labeled data set that you're sending. Again, it's again working on a set of features, and each of these layers is going to be sensitive to one particular feature or some particular aspect of your data parameter space. And because it's labeled, you are actually doing a fit. So you're basically optimizing each of these layers by feeding it labeled data set where you're absolutely sure what each data set is, that you definitely know that this is a candidate, you definitely know this is an FRB, you definitely know it's RFI. And then once you train it in the sense that now you're kind of setting weights on each of these layers, then you can use that neural network as is to then classify newly incoming data, right? Because then you're assuming that now it's fully trained, it should be basically be able to run without any issues. It should be able to classify everything without making any mistakes. Now, of course, in reality, that's not true, but we have managed to get to accuracies that are much, much better than what you would with standard unsupervised machine learning techniques and other classifiers that I mentioned. So just to kind of give you a rough idea, so one type of neural network that is commonly used in fast radio transient searches is the convolutional neural network. So we've already talked about convolution in like match filtering. So you're basically, it's like a filter, right? You have a kernel that you're running over your data set that is fine-tuned to pick up some feature, whatever is of interest to you. And so what you do is, in your neural network, you're just basically, let's go back. So you have a convolution neural network, which is just one layer of neurons, say. Let's say you're feeding it an image, right? And an image has information on different length scales, different spatial frequencies. And each of these layers is going to be a convolutional kernel, which is going to be fine-tuned, or how do you say, is going to be sensitive to one particular spatial frequency or a range of spatial frequencies and spatial scales in your image. And then once the convolution is done, we do something called as max pooling, where you take your convolution values and you're basically extracting out the most, how do you say, or the highest value in that matrix, in the sense that the feature that actually stands out. And then you then send that bit to the next layer, and so on and so forth. And so, for example, right, I'm showing you this little picture of a cat. So if you send this image to a convolutional neural network with different layers, you can see this is how the resulting image looks like after a run of convolution and max pooling from different layers. And you can already see that every convolutional layer has picked up on different length scales of the image and also different spatial scales. And you need all of this information to finally, for the neural network to then identify that it's a cat or something else. You can't just because if you use if you don't use too many layers, for example, it might only have this information and it won't be able to classify it, right? If you have too many layers, you're unnecessarily wasting computational power. So you have to do a bit of trial and error here as to how many layers of convolution neural network you actually need in terms of optimizing not just for accuracy, but also for the speed, right? Because that's also an important ingredient here that you have to consider. Yes. Yeah. But after the max pooling, you're still storing all the pooled features for the very end as well. Okay. Yeah, but the convolution is happening on the original lens. Yeah. So let's go to our case now, right? I showed you a cat. Now let's actually look at some real data, right? So here is an example of a real pulse, right? This is actually a real pulse from the Meerkat radio telescope. So you can see there's a nice dispersion sweep here. The DM is like about 63. You can see after de-dispersion, single pulse, broadband. This is what a human classifier sees, right? When you are trying to identify something. So what we do is we convert this into this space here, where, this is just an example, right? This is, I'm showing you like a real life example where what we are doing in our case. So here you can see you have seen this dispersion time curve right now in the transient X outputs as well, right? So you have dispersion measure, trial dispersion measure and time, and the grayscale is just showing you the intensity of the signal to noise ratio. And at the right DM, you can see it peaks here at the right DM and the right time. And this is, again, just the same thing here, which is frequency and time. And this is RFI. Now we know that a real source actually has this characteristic DM time curve, which we call a bow tie, right? It basically looks like a bow tie if you look carefully. And RFI signals will not show that because they don't disperse with a new square root relation. So this is RFI, right? You can see, and this is real data. This is the kind of stuff that we have to go through in real telescope data. And you can see it's all over the place here. So you can easily tell by eye that it's RFI and it's not FRB. So why not just feed it to a neural network, you label it, feed it, and train your neural networks to identify this exact thing. And so that's what has been done. So Fetch was probably one of the first convolutional neural networks that was implemented specifically with the goal of finding fast radio transients in mind. That's the one that you're using today in today's workshop, and you will be later today as well. So this is just kind of a schematic of the different convolutional layers and how the data step through. So you can see there is a DM time curve here, and this is the for the candidate, and this is for the RFI. So DM time is the first one. The second one is just the frequency time. So those are the two images that we're using as a feature space for the neural network. And again, it goes through these different layers and will give you an output. So what will output in the end, if it's a trained network, is it will output a probability of something being an RFI candidate and something being, an FRB or something astrophysical. But now you can go one step further, right? So we spoke about neural networks here trying to identify FRBs and RFI. But all of that is happening at the very end of a search pipeline, right? So you have telescope data coming in, you're de-dispersing, you're doing a match filtering, you're getting candidates, and then you're classifying. But then you can also ask the question, why not skip some of these steps in between and just directly let the machine learning class or the neural network find things directly in the data? So what you can do is, as you're streaming data through, right, it's as a function of frequency and time, you can directly convert it into a DM time lane, right? So you're basically directly going from input data directly to something that looks like something like this. I guess something like this. I'm not going to go into details of this neural network, but the point I'm trying to make is that instead of building a time series for every DM trial, then running a match filter, trying to then find candidates for every DM, you can just convert your frequency time space into a DM time space, and then just ask your neural network to look for bow ties in there, anywhere in the data. So you're literally skipping all of this stuff. So you're from the de-dispersion stage, you're directly going into machine learning or neural network. And then it can just find these bow ties anywhere in your data set. And it's saving you a lot of time, and it will be also very accurate. So your false positive rate is going to be very small as well. And so nowadays, people have started to implement these neural networks, which basically directly go from de-dispersion all the way directly to candidate identification and classification. So you're basically just skipping a lot of this, saving a lot of, again, time, energy, and compute power. So I think I'm going to end there. I think it's my last slide. These are some of the papers, if you're interested, you should definitely check out. And some of the software that's already publicly available for you to also kind of play around with. I would highly recommend doing that if you are interested in finding fast radio transients in telescope data. And I think this is a kind of good stopping point now for the next part of the workshop, which is that at this point we have gotten to a point where you have you're getting candidates from your single pulse search pipeline. You've gone through all the candidates visually. It's easy to do that, in a small data set that the one we have, where you have like 10, 15 candidates to go through. But now you will also see the power of AI, because then you can do the same thing and run. I think in this case we are using fetch. Run fetch on this and see if fetch is able to identify the same candidates that you were able to identify visually as well. Okay. One thing I would like you to think about is, how would you assess or quantify the performance of a classifier, right? I mean, I talked a lot about accuracy and stuff, but if you want to quantify it, how would you do it? Okay. I mean, it's very simple. There's nothing complicated, but when you're actually doing this exercise, do try to think about this. And I'm happy to discuss this further if you're keen, but yeah, I think that's all I have to say.